Hi, my name is YongKyung, PhD candidate at UNIST. I will deliver the presentation of time delay estimation of traffic congestion based on the statistical causality. So the traffic congestion is occurred by many reasons. For example, traffic incident or kind of construction and the weather change. But it is very hard to estimate the propagation of the traffic congestion. So especially we are interested in the traffic congestion occurred by the traffic incident, and it propagate along with the following road with some time lag, but it is very hard to estimate. But at the same time, it is very important factor for the navigation service provider. So as you can see the figure, the speed reduction is occurred from the route road to the following road. The black line indicate the road speed of the incident occurred, and the other graph indicate the following road. So there is a specific time gap between the route and the following road, such as Hope 1, Hope 2, and Hope 3. So by estimating the time gap of the condition propagation, it is able to estimate the start time of the congestion on the following road. So our objective of the research is provide model-free method to estimate the congestion propagation delay using the transfer entropy. And also we try to quantify the certainty of the estimated time lag using the bootstrap method. So this is overview of our research. So at the left figure, you can see the star indicate the incident location, and the road segment A is the incident road or route road, and B, C, D indicate the incoming road, which is Hope 1, Hope 2, and Hope 3 road. So in the right figure, you can see the speed drop according to the incident. So the blank line indicate the traffic speed of the road segment A, and 1, 2, 3 indicate the road segment B, C, and D. So you can see there is a time lag, and in the figure in the bottom, we propose a method to estimate the time lag between these roads. For example, in case of the incident road and Hope 1, there is a time lag around 3 to 4 minutes. And in case of road segment D, it is much far from the incident location, so it has around 20 to 22 minute time lag of the congestion. So this kind of causality analysis is very common in the traffic situation and also in some other domains such as like finance. So causality analysis can be categorized into two topics. The first thing is the analysis about the random variables. So it is comparing the one factor and the other factor, and it analyzes the causal relationship between two variables. And the other category is analysis over the time series data. So it is it analyzes the relationship between the two stochastic processes. So in the right figure, I found the recent research using the transfer entropy to estimate the causal relationship between the sentiment of the investor and the returns. So you can see the sentiment from sentiment to the return, there is some time lag exists. And in the figure in the bottom, you can see the transfer entropy is higher in the blue line. So it means that there is a causal relationship from the sentiment to return, but the reverse direction is not valid. So we have insight from this example. So first thing is that we can estimate some specific time lag between two time series. And second thing is that we can define the causal relationship between two time series, especially it is not a symmetric relation, but we can know the direction of the causal relation from the one factor to the other. So we use the transfer entropy. So it is kind of formulation of the conditional mutual information. So it is also known measure of the information flow using the Shannon entropy. So it is designed to characterize the statistical causal relationship between two variables. So for time series variable I and j, the transfer entropy in the direction from the j to I is defined as follow. And by the Martinsky, the effective transfer entropy is proposed because when you compare just two time series, there might be fluctuation by noise or other factors can affect. So the effective transfer entropy use the shuffled version of the time series J. So it generates more robust version of the transfer entropy to estimate the causal relationship. So we try to find the real time lag you had to maximize the effective transfer entropy in the equation in the bottom. And for the analyzed time series, we apply the nonlinear normalization with the sliding window. So there is two techniques combined. The first thing is the nonlinear normalization, and second thing is using the sliding window. The purpose is to handle the scale and nonlinearity and non-stationary time series with more efficiency. So as you can see in the equation, so we compare the percentile value of the low time series. So in the figure, you can compare two time series with the black and the red line. And basically, it has different scale and different characteristic. So we transform it into the same range from 0 to 1. So when we test the effective transfer entropy with the raw data or the transform data, you can see the different result of the certainty. So you can see that the normalized version has higher certainty of the time lag in around 10, and we generate this data with the true time lag with 10 minutes. So when we apply this transformation, we found that the proposed method using the transfer entropy worked better to estimate the true time lag. And furthermore, we apply the bootstrap approach to quantify the estimation. So we generate the random bootstrap sample and generate the distribution of the estimation in the figure B. So figure A might be a true time series, and we divide the trend and the residual of the time series, and we shuffle the residuals and generate the new samples as like x prime and y prime, and estimate the time lag of each pair. Then we can generate the distribution of the time lag as well. So through this process, we can find some causal relationship between two time series, but as I explained in the research background, there is some load segment in the traffic network. So we try to define the significant causal relationship of two loads using two criteria. The first thing is that when you generate this kind of distribution of the time lag, then there might be the mean value of distribution and the standard deviation of this distribution. So the first criteria is the standard deviation should be lower than the threshold value. And the second criteria is if the road is close to the root road, then it should have the lower time lag compared to the next incoming road. For example, in the figure, the Hope 1 has around 3 or 4 minute time lag, but the Hope 2 has 7 to 8 time lag. So it is obvious that because the Hope 2 is much far from the root road, so it should have more time lag. So based on this understanding, we conduct several experiments. So the first thing is the simulation data that I showed before the previous slide. So the true time lag is 10 in this case. And we compare some techniques to transform the time series. So we can decompose the time series or not. So as I said, we can decompose the time series of trend and the residual. And when we apply the decomposition, then we can distinguish the true trend of the time series. So it is more opaque to the estimate the true value. And we compare the normalization technique. So we can apply the normalization without sliding window and with the sliding window. So we compare 3 normalization, the min-max, z-score, and the nonlinear. And we compare the sliding window technique from 10 to 40 window. So in this case, the nonlinear normalization with sliding window size 20 show the best performance with MA is 0.94. So I will describe the example of the nonlinear normalization and other normalization technique with or without sliding window. And you can see the figure F, our proposed transformation works better compared to the different normalization approaches. And also we apply this technique to the real world data. So we use the traffic information in the Seoul, and there is around we analyze around 30,000 road segment, and there is around 3,000 incident occurred, and we analyzed each case and the causal relationship of each road segment. So, for example, when we analyzed an incident and the Hope 1 relationship, the average time delay is 8.95 minutes. And if we consider the Hope 3, then it is increased. So this is the specific case. So the incident occurred at row segment A, and we can generate pass 1 to pass 5. And we compare the mu value and the sigma value. And we use 2 different benchmark methods called TLCC and DCCA. The former one is time-lagged cross-correlation, which is used the Pearson correlation. And second one is detrended cross-correlation analysis. Both method is well-known method to estimate the time lag, but they cannot provide the certainty of their estimation. But compared to that, our method can quantify the certainty of the estimation using the sigma. So for example, in pass 1, the sigma value is very high. It means that the estimation is not significant. But in case of pass 5 or 4, the sigma value is low in Hope 1, Hope 2, and Hope 3. So we can conclude that the incident affect to the pass 4 and pass 5, and it propagate along with these passes. So here I selected some passes. So in case of pass 1, the sigma value is very high, but in case of pass 3 and pass 5, the sigma value is low, the distribution is more dense, then it means there is some specific and significant time lag between these two roads. So for pass pipe, the time lag of estimate from hop 1 to 3 are around 8 or 15 and 20 minutes respectively. So in this research, we propose a method lag-specific transfer entropy estimator using some time series transformation technique. So the proposed time delay estimate help to quantitatively understand the propagation of traffic congestion. And we also apply the bootstrap approaches to and its density estimation of statistical functional enable the certainty of the time delay estimate. So we thought that this method is very useful for the GPS navigation systems and navigation service provider. So we will expand the further research using the real world data to estimate the true time lag of the congestion. And this is all, and thank you for listening.